Okay guys, like you watched in the video, we are going to start our next unit, which is on log functions. And so log functions and exponentials, they kind of go together, obviously, from what you saw on the videos. They're inverses of each other graphically, so I'm going to show you that on the front page, but then you actually use them. They're pretty much the same thing. So you use them interchangeably, so we can go from exponential form into log form and log form into exponential form. And that's our goal today, is to be able to evaluate it using exponentials when it's in log form. So you'll see it's kind of converting from two different forms when it comes to types of equations. So let's take a look here. If we're going to graph this, now as a reminder, this is exponential, okay, and it's growth because the base is 2, so it's bigger than 1. So let's see, if we were to do a table of values, right, even without our calculator, all this means is we plug this in and we do that math, we get 1.5. So I'm just plugging the x in. We do to the 0 power, you get 3. We do 3 to the first power, we get 6. And we do to the second power, and we get 12. So I just used my calculator by plugging in those numbers and got those. So let's do a graph of this exponential function here. So we're going to plot the points: -1, 1.5, 0, 1, 2, 3, 1, 1, 2, 3, 4, 5, 6, and 2, 1, 2, 3, 4, 5, 6, 9, 10, 11, 12. Okay. Now remember, because it's exponential, it's going to have a horizontal asymptote, and it's going to look something like this. So let's go down to the bottom of the paper here where it says properties of the original function. So properties of the original function. Well, a couple things. Remember, the original function is exponential because the x is the exponent and its growth, which we just covered. Exponentials did a lot of them, which means it has a horizontal asymptote. Now, because this is the parent function for the most part, guys, looking back up here, there's no h and there's no k. And since the k is 0, the horizontal asymptote, and you can see it right here on the graph, it's going to approach y equals 0 and never cross. So it's never crossing the x-axis. The domain is all real numbers, because all exponentials are always going to go to the left and always go to the right just really slowly. The range goes with the asymptote, so 0 to positive infinity. And you could see, if we were looking at the y-intercept of this graph, the y-intercept itself is right here at 3. So 0, 3. So now we're going to look at what about talking its inverse, which ultimately is going to be a log graph. So they are called logarithmic functions. Kind of a strange ones. Now, inverses, remember, are supposed to be opposite. So really, an inverse here means that it's reflecting over a particular line, and the line it's going to be reflecting is over y equals x, and I'll show you that. Let's do the graph in the inverse. So basically, we're going to take these points up here for the exponential, and we're going to flip them. So the first point here is going to be 1.5, -1. And then the second point is going to be 3, 0. So we're just flipping the original ones to make it the inverse. And then for graphing, let's just go ahead and plot these points. So 1.5 is about here and -1. 3, 1, 2, 3, 0. 1, 2, 3, 4, 5, 6, 1. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 2. So you can see this one is not going in the same direction as the original exponential function. This one's going to look something like this when you connect the points. Now, it's not going to actually cross the y-axis. So right away, okay, this inverse of the exponential is not going to have a horizontal asymptote if it's never going to cross the y-axis. Instead, it's going to have a vertical asymptote. So these log functions always have a vertical asymptote. And in this case, because it's a vertical line, you're not going to say y equals, you're going to say x equals. And in this case, it's x equals 0 because the y-axis, that's the equation for it when x is 0. Now, from here, it also switches up domain and range, okay? The domain for these, if the asymptote is at x equals 0, we can all see x is never negative. It's going to stop here. So then the domain is actually from 0 to positive infinity. See how they kind of swapped? The range on the exponential was 0 to infinity, the domain. But here, the range for these, this is always going to go down, okay? Believe it or not. And this is always going to slowly go up. I know it's hard to see. It's going to slowly go up. So the range for logs functions is all real numbers. So you can see right here the swapping, and that pays a big difference because they're inverses of each other. And then look here. Instead of a y-intercept, it doesn't hit the y-axis, but look here. It has an x-intercept. And the x-intercept is at 3, which versus the exponential, the x-intercept, okay, didn't exist, and the y-intercept was 3. So you can see, guys, this is the log graph. We call them logs. And this is the exponential. Now, today we're not going to focus on the graphs themselves to kind of show you visually. We're going to actually talk more about how you convert from exponential form into log form and what does log form look like. So let's turn the page here. Okay. So again, okay, the inverse, so the opposite of an exponential function has a special name. It's called a log function. You're going to be seeing that. This is the one where it had the word log in it. You've already seen the parent function equation on the packets when we did our A, H, and K shifts. So now, why are logs useful, right? Well, basically, they can solve exponential equations. We can convert them. Now, this is just one type. You could do algorithms, guys. So logarithms where it actually is in software developing and things like that. But we're just doing the basic of these with graphing and how they are. But more advanced math, you can get into that type of stuff with them. Now, here's what I mean. Okay, like this. If I give you this equation, 4 to the x power equals 64, I think everyone in here could say 4 to what power makes 64? Clearly, the answer is going to have to be 3 because 4 to the third power is 64. So the answer would be 3 to that equation. Again, we didn't have to do any math other than in our head, right? But something like this, 3 to the x power equals 10, there's no way to come across it. Now, we could approximate, okay, but there's really no way to get the exact decimal. Like 3 squared we know is 9, okay, and we know 3 to the third power is 27. So clearly this answer is going to be between 2 and 3. But how do I know the exact answer? Is it 2.6? Is it 2.8? I don't really know until we start using what's called a log. So that's what we're going to focus on today. Converting from exponential form into log form and vice versa. Go over the two forms. Exponential form. Y equals, it has a base and x is the exponent, which we've seen. The log form, okay, looks like this. And you can convert between both of them. The log form, you put the word log, that's how you know it's log form. And then you say log base. So the base, see this base, it goes right here, of whatever this is, equals the exponent. So we would read this as log base b of y equals the exponents. So like a lot of the videos say, logs equal exponents. Okay, and we use this method that's called the loop to rewrite these. And that's what we're going to practice today, using this loop method to go from one form into the other. So, if we take a look here at the bottom, evaluate. When it says evaluate, guys, your ultimate goal, if you're evaluating a log, is find an exponent. It's basically what you're doing. You're trying to find an exponent, guys. So, okay, when you read this out loud, the easiest way is to convert it to exponential, so you can try to figure it out. So let's say we say, put an x here. When we're trying to figure out what is this here, log base 2 of 16 equals something. That's why I put an x. Well, really, to read this, guys, you would do the base is 2. So we're going to rewrite it into exponential form. 2 is the base, and this is how the loop works. So it's asking 2 to what power would equal 16. It's always loops like that. So we're able to evaluate the log and write it in exponential so that we can answer the question. So this has to be 4 because 2 to the 4th power, so x must equal 4. 2 to the 4th power is 16. But again, that's what you're trying to do here. So you're trying to say 2 to what power makes 16. Same thing if we look at number 2 here. And I think now with this one, we probably won't have to write it out all the way. But 9, this is a base of 9. So log base 9 of 81. 9 to what power makes 81? Clearly, we all know it's 2. That's how you're reading it. So you're reading it in terms of exponents. Reading it in terms of exponents. Here, 6. So basically, again, when we do this loop method, this is kind of what we're asking. 6 to what power would make 216? You're trying to find the exponent. Well, clearly, 6 to the 3rd power would make 216. So 3 would be your answer. That's basically what you're doing when you're going from one form into the other and evaluating a log. So here, 5 to what power would make 625? Well, I believe, I'm checking it right here. And you could use your calculators for these. I mean, some of them, we get used to it. So it's 5 to the 4th power. So my answer would be 4. Now, 4 and 5 are a little trickier because you could see we're sitting there asking for a whole number base. So 7 to what power, right, if we did this around, would make this. And it would be the same question down here. So 5 is the base, so log base 5. So 5 to what power makes this? Well, let's start with 5 first. This one, think to yourself, 5 to the 2nd power makes 25 over 1. So the only way for it to flip, and we talked about these with graphing the exponentials, is having a negative exponent. So this would have to be -2. So the answer to this one would have to be -2. So negative exponents will flip and get a fractional answer like this. Same thing with here, okay? 7 to the 3rd power is 343 over 1. But we want that flip, so it has to be to the -3rd power. So that's going from one form to the other, and that's going to be our ultimate focus. So we just have some more stuff and some common stuff, and I'm going to show you some stuff in the calculator, but we're trying to focus on logs today. So let's turn the page, and let's take a look. So now, again, just rewriting. Now, you're not actually evaluating here. I tell you the answer. See, I tell you it's going to equal 5, just to practice this loop method. Okay? The loop method is a really good way to just keep rewriting from one form to the other, and especially next class when we start divisions involving these processes, it's going to be important to know this method. So 2 to the 5th power, see that's how it's written, in exponential form, will equal 32, which again, you're not solving here because I'm telling you it equals it. If I had put this just that, you would have to give me the number 5. Here, same thing, rewrite it to exponential. 5, base 5 to the 0 power equals 1. Remember, this is a true statement. Any exponent of 0 will equal 1. Every time, any exponent of 0 will equal 1. Here, 3 to the 4th power equals 81, just like that. Here, even if it's a fraction, that's still the base, so 1/2 to the -1st power is going to equal 2, which is going to equal, remember, negative exponents flip the base. Now, let's take a look at the calculator. Let's take a look at some important basics of logs. In your calculator, you have 2 buttons. All right, guys? If you look here, next to the 7 and next to the 4. I know it's a little hard to see on my calculator. Next to the 7 is the word log. Next to the 4 is what's called ln, which is called the natural log. The common log, guys, always has a base of 10. They will never write that, okay? So look here. Log 10 means, put a little 10 down here. They're never going to write that. This means 10 to what power, so I'll put a little box, equals 10. See, they're not going to write the little subscript or the base of 10 next to the word log. That's always going to be there. That's called common log. And this answer would make 1 because 10 to the first power makes 10. Same thing here. Again, they're not going to write log with a little base of 10. That's going to be common log. So even in your calculator, if you wrote log 1, it's going to give you 0. And the reason for that is because, guys, it's the calculator's doing the math of base of 10, which goes with the common log, to what power equals 1. That has to be 0. That's the only number, because again, the exponent of 0 is what makes the 1 here. So notice they will not have the little 10. So if you just see, for example, log of 100, just an extra example of it, this is saying 10 to what power makes 100. It's never going to write the little 10 there. Okay, keep that in the back of your mind. The other one on the calculator there is ln. ln goes with e. So these are common logs. And then this is called natural log. So when they realized that they were doing the e, which we use for compound continuously, they realized they need an inverse of e. So they created ln as inverse of the e. Okay? E goes with exponentials. So when you see e in the problem, it's exponential graph or growth like we did in the word problems, but while ln goes with logs, if you had to classify them. So you can take this, guys, and literally notice that they're not going to put a little e here. Next to the ln, if you put ln base e like this, little tiny e, they're not going to do it. But when you're reading it and you convert it to exponential form, it's saying e to what power makes 1. Just like we said, anything to the 0 power equals the 1 there. And look, you could check it in your calculator. If you hit the ln key, which is next to the number 4, and put in 1, it's going to be 0. Because that's what the calculator is doing. E to what power, which is e to the 0 power, makes 1. Same thing here. If you notice this, they're never going to put the little e here. So e to what power makes e? Well, the only way to get itself is like the common log. It has to be a 1. And if you ever forget, ln, and then second division is the e, and you get 1 out of it. We're going to continue to work with it. I know it seems like a lot right now, but you'll get some chance to practice. And I promise we're going to keep practicing this loop method and reading it from log to exponential form. So the last thing for the notes, if we look on the last page here, is let's go and so we've been doing log form to exponential. Let's take from exponential into log. So we're going to write all 4 of these here with the word log in it. The base is always your biggest thing to pick out, and then we're still going to do the loop, guys. So here would be log base 5, and you put it down there, which is this base of the exponent, of 125 equals the exponent. Logs should always equal whatever the exponent is. Even if there's all letters here, as long as you could pick out the base, which is a, so it's log base a, then we loop around of c, so you kind of make it a little bigger there, equals the exponent, which they denoted as b. Logs will always equal exponents. Logs will make your exponents for you. Now, even if you have to go a little backwards, don't fret. Like here, this is still the base of 16. So log base 16. Then you're going to go this way. Of 8. If you don't have to put the parentheses there if you don't want, completely up to you. Equals the exponent of 3/4. Logs will always equal the exponent. Here, okay, find the base. Here's the base, because there's the exponent with it. So log base 7. Again, now we're going this direction. Of 3 equals the exponent. It always equals the exponent. So in this case, it's 2x plus 1. So the whole purpose of going from one form into the other is if you have to find an exponent, this is the way to do it. So last but not least is, let's say you have problems like these. Now notice there's no equations with these, okay? So what they're going to be asking you to do is evaluate. If it says to evaluate the logs, okay, this means find the exponent. Is basically what it means, guys. Find the exponent. So in order to do that here, like if we read this out loud, this means 4 to what power makes 10? Again, like we kind of started at the beginning, I don't know what this is. It's going to be a decimal exponent. For this to work, guys, we're going to use what's called, put over here, change of base formula. Okay, we're going to use what's called the change of base formula. So here's what it means. Let's say you have a log that we can't figure out, like this one. I can't figure out the exponent. So log base b of something. Well, your calculator will help you, okay? What you can do is if you take the log of the bigger number, so in this case I called it y, and divide it by the log of the base. So the base goes to the bottom of the fraction. In the calculator, by doing that, it will give you the decimal exponent. So again, by doing this, it converts it to base 10, as they call it. So it basically converts it in the calculator to give you the decimal exponent, okay? So in order to do that, it converts it to base 10 and finds the exponent for you. So for instance, if we take a look here, right? Again, I couldn't do this in my head, so the only way to do it is because it's going to be a decimal, is let's do the change of base formula. So for the first one, I'm going to do log 10 divided by log 4. See, the base is at the bottom, the bigger number is at the top. You can literally type that in your calculator and it will give you the decimal exponent. So log 10 divided by log 4. There's your decimal exponent. So we can round it as 1.66 if it's being rounded, okay? That's the idea. And look, you can check your answer, guys. If you do 4 as the base, raise to the, and then look, just hit the, don't round it, because if you round it, it won't give us 10. Our goal is to get 10. So what we need to do is if you hit second and then the negative key, see how it says the answer, second negative? It's going to take this big decimal, it's going to keep going on going, and put it up there, and you'll get 10. So you can see they're opposites, and that's how it works. The exponent would have to be 1.6, so 4 to this weird power makes 10. It's the same thing for any ones you can't figure out, okay? If you get a calculator, you can do the change of base. It will convert it for you to a base of 10 automatically, and it will find the exponent. So here, I could do log 11 divided by log 6. Log 11 divided by log 6. And that exponent is about 1.34. Same thing here. Now remember this one though, see, this one doesn't have a number with it, right? So this is common log. What that means is you don't even have to do change of base. You could literally just type it in your calculator. Log 120. And that is it. So what it's asking again, guys, is 10 to what power makes 120, right? I have no idea, but there's my answer. That would be my answer, about 2.079. That exponent, and again, you could check it. 10 to that answer, second, and you get 120. And last but not least, change of base. So you only have to use change of base, guys, if the base is not 10 and you can't figure out the exponent in your head. So log of 135 divided by log of 15. Because again, I do not know 15 to what power makes 135. I have no idea. So this formula is going to convert it to a base of 10 for me and help me find the exponent. So log 135 divided by log 15. And there is my decimal exponent. So you can see, guys, the purpose of logs are to find exponent answers, and that's what we're going to be doing even in next class, basically, is to solve problems with it. So now take like about, let's say, 5 minutes or so, okay, and see if you can do the same thing for this practice sheet. I'll have the video with the answers up. Again, your whole purpose with this practice sheet that's attached here is 7. You're asking yourself 7 to what power makes this? And that's what you're doing for all those to kind of see. And then the last, number 10, is basically use that change of base formula with your calculator. So take about 5 minutes on this, and then I'll do a quick video recap of the answers.